In the next few minutes, I'll show you what a transformer actually is, why the architecture's before it hit a hard wall, the one idea at the center of it called attention, what queries, keys, and values really mean, why we use many heads instead of one, the three flavors of transformer behind every model you've heard of, and why this single 2017 paper rewired the entire field. Welcome to Concept Stack. We produce one concept a day, and each one stacks on the last, building the framework for AI together. Let's dive into transformers. Here's the thing. For 4 episodes, we've been talking about everything around the model. Tokens, embeddings, vector search. None of that is the model. The model is this box in the middle, and inside that box is one architecture, used by GPT, Claude, Gemini, Llama, Mistral, every embedding model, every speech model, and most image models too. It's called a transformer. By the end of this video, you'll know exactly what it does. Before 2017, the standard architecture for language was a recurrent neural network. RNNs and their cousin LSTMs read text one token at a time, left to right, carrying a hidden state forward. The problem was structural. Token 100 had to wait for tokens 1 through 99 to finish before it could even start. You couldn't parallelize across the sentence, which meant training on a GPU mostly wasted the GPU, and the hidden state forgot. By the time you reached the end of a paragraph, the early context was gone. People had been fighting this with bigger LSTMs, gated cells, attention patches bolted onto the side. None of it really worked. Sequence models had been stuck on context lengths of 50 to a couple hundred tokens for years. The whole field was waiting for someone to break the dependency. The breakthrough was a single idea. Instead of forcing tokens to be processed in order, what if every token could just look at every other token directly, in parallel, and decide for itself how much each of them matters? That's attention. For every token in the sentence, you compute a weight against every other token, and those weights tell the model which tokens to pull information from. No order, no bottleneck. The model learns the weights from data. Everything downstream falls out of this. Here's self-attention in 5 lines. You start with your token embeddings, the matrix X. You make 3 different projections of X, called Q, K, and V. Q is what each token is looking for. K is what each token has to offer. V is what the token actually contributes if you decide to pull from it. You multiply Q by K transpose to get a score for every pair of tokens, divide by a constant to keep the numbers stable, and softmax to turn them into weights that sum to 1. That weight matrix is the thing. It says, for every token, how much of every other token's value to mix in. Multiply by V and you've got your output. Take a sentence like, the cat sat on the mat. When the model processes the word it, the attention weights light up against cat, because the model has learned that pronouns usually attend to the noun they refer to. That's it. That's the entire trick. Every modern model runs this loop, in every layer, on every token, in parallel. One attention pattern only captures one kind of relationship between tokens. Real language has many. There's syntax, which word is the subject. There's coreference, which pronoun refers to which noun. There's topic, tense, sentiment, and so on. The fix is multi-head attention. You run 8, 16, 64 parallel attention computations, each with its own Q, K, and V projections, each free to specialize on a different kind of pattern. Then you concatenate the outputs. Same compute budget, far richer signal. Every modern transformer uses this. A real transformer doesn't just do one round of attention. It uses a repeating block. Each block has multi-head attention, then a feed-forward layer that processes each token independently, with layer normalization and residual connections wrapped around both. The residual connections are the dashed lines. They let information skip past each layer if it's not helpful, which makes stacking deep networks actually trainable. You stack this block 12 times for a small model, 32 for a mid-size one, 96 or more for a frontier model. That stack is the entire transformer. The same transformer block can be wired 3 different ways. Encoder-only models read the input all at once in both directions and produce a vector representation. BERT and most embedding models work this way. That's what generated the embeddings we talked about in episode 3. Decoder-only models generate text 1 token at a time, left to right, only attending to tokens before the current one. That's GPT, Claude, Llama, every modern chatbot. And encoder-decoder models do both, encode an input sequence, then decode an output sequence. Translation and summarization started here. Same block, 3 wirings. There's one thing missing. Plain attention has no idea what order tokens come in. Dog bites man and man bites dog would produce identical attention scores, which would be a disaster. The fix is position encoding. You add a small position-specific vector to each token's embedding before it enters the model. That way the same word at position 0 and position 5 shows up as a different input. Modern models use a fancier version called rotary position embeddings, but the principle is the same. Tokens carry their position. The reason transformers took over is they scale. Every token's processing happens in parallel, which means a GPU can run a transformer at roughly the GPU's full throughput. RNNs couldn't. And when you scale a transformer by adding parameters, training data, and compute, it just keeps getting better. There's a whole branch of research called scaling laws that tries to predict in advance how much more capable a model will be at 10 times the parameters or 100 times the training tokens. So far, the curves have not bent. Doubling the compute consistently produces a measurable gain in capability, with no plateau yet found. Same architecture works on text, on code, on images, on audio, on video, even on protein structures. The original paper, Attention is All You Need, has been cited over 130,000 times. There is no second place. Once you know transformers, the modern AI landscape stops looking like 100 random models and starts looking like one architecture in 100 different outfits. GPT is a decoder transformer trained on text. Claude, the same. Llama and Mistral, the same. Stable Diffusion uses transformers inside its image generator. Whisper, the speech model, is an encoder-decoder transformer. AlphaFold uses transformers to fold proteins. Robotics models use them to plan motion. The differences between them aren't the architecture. The differences are the training data, the scale, the fine-tuning, and the way input and output are represented. The blueprint underneath is the one you just learned. That's the end of this concept, but each video stacks on the last. Subscribe, and we add the next layer tomorrow. So that's transformers. The architecture every modern AI model is built on, the trick at its heart called attention, and why a single 2017 paper rewired the field. You now know the building. But how does the building learn? How does a fresh transformer with random weights become a model that can write, code, and reason? Tomorrow, pre-training. The trillions of tokens, the loss function, the compute, and the moment a network of weights starts to look like something that thinks. Thanks for watching.